Hello everyone, thank you for coming to my preliminary exam presentation. I'm Xingjian from Vikas Group, and my thesis topic is Deep Learning on Manifold-valued Data with Applications to Neuroimaging and Natural Images. Consider the machine learning setup. We feed data X into the model theta, and then the model will give us an output Y. Formally, we can write the following equation, y equals to f theta x. To simplify the learning algorithm, we normally assume that model space theta and data space x are both Euclidean. For some models, such as neural networks with no constraint, the weight for one layer lies in Euclidean space. But for some models, we know that they are not Euclidean. For example, some distribution families. On the other hand, for data space, we can have multiple sources of data, like images, documents, speeches. We can assume that they lie in Euclidean space. For images, if we look at RGB channels, they are Euclidean vectors. But there are also many more data space that are not Euclidean. Graphs, shapes, spheres, they are not Euclidean. Even if we consider HSV of color images, it will no longer be in Euclidean space. So we will need some mechanism to deal with the non-Euclidean data. In this thesis, I will focus on one special kind of non-Euclidean data, manifold-valued data, which is smooth and has some benefit. What is the main difference between manifold-valued data and Euclidean data? For Euclidean data, we can easily apply multiplication, addition, and stay inside the same Euclidean space. But for manifold-valued data, even these simple operations are not satisfied. Thus, to build a model for manifold-valued data, we need to make some more modifications. This is the scope of this thesis. For the data type, we will mainly work on the manifold-valued data, and also show that our proposed method can work on Euclidean space as well. For the application-wise, we will focus on the application of both natural images and neuroimaging, as neuroimaging naturally form the manifold-valued data. Let's look at the first use case, dilated convolution neural networks for sequential manifold-valued data. To measure the structure of the brain, the patient needs to stay steady in the machine for a while to get the raw diffusion MRI data. The data is acquired by applying strong magnetic field gradients along different angles. If we look at one specific voxel of the brain, there are two diffusion types. If there's no fiber bundles around that special location, the water molecule can diffuse freely. However, if there's a fiber bundle around, the water molecule can mainly diffuse along that fiber direction. We can use a Gaussian distribution to fit that distribution pattern, where the covariance matrix represent the diffusion direction. If we measure all the locations inside the brain, we can get the diffusion tensor imaging called DTI. As the nature of 3x3 covariance matrix, it considers only about one major direction. Thus, the angular resolution is relatively low. But the good part of DTI is that it only requires 7 to 9 minutes scan time. On the other hand, if we want more accurate angular information, for example, when there are two fibers across at the same location, the DTI might not be accurate enough. In this case, we can use a distribution function over the sphere to measure the probability of the water molecule to diffuse along that direction. If there's no fiber, the distribution may be like an uniform distribution. If two fibers crossing each other, there may be 4 peaks over the distribution functions. Similar as DTI, if we measure the distribution function at every location inside the brain, we can get the orientational distribution function called ODF. The biggest benefit of ODF over DTI is the ability to measure the crossing. Also, the angular resolution is much higher for ODF. But to get a clear ODF, it would require much longer scan time, 35 minutes. It's 5 times longer than DTI. By applying the tractography method, we can track the fiber bundles of the brain to study the connectivity of the brain. This is important to leverage the macrostructure of the brain. In this chapter, we will focus on the fiber bundles, which forms 1D sequential manifold-valued data. Speaking of sequential data, we can always apply an RNN model to recursively fit the sequence as language model does. But this suffers gradient vanishing and longer training time. On the other hand, in the computer vision, we have CNN model as moving kernels. Can we use it in the sequential models? Well, traditional CNN has some limitation regarding to the view field. There's a special type of CNN called dilated CNN, which have holes in the kernel, and thus can increase the view field without increasing the depth of the network. The benefit of DCNN model is fast in training and no vanishing gradient. But for the manifold value, such as SPD metrics in DTI or distribution functions in ODF, all the basic operations within DCNN need to be updated. A first attempt will be vectorize the SPD matrix and apply matrix multiplication afterwards. However, the output may not lie in the same manifold space anymore. So, what operations are needed? In deep learning models, we encounter with major of 3 operations: multiplication, addition, and activations. For multiplication, we can substitute the weighted sum to weighted mean and apply the geometry distance to iteratively compute the result. And for addition, we can substitute it with the group operation so that it will remain in the same manifold space. Finally, as manifold already includes nonlinearity, we will not need nonlinear activations. To compute the weighted Fresher mean, we use a recursive model. There's a proposition saying that the recursive model will converge. To build the DCN model, we further extend the convolution, the linear layer, and the skip connection layers. For the experiment, we want to test the group-wise difference between preclinical Alzheimer's disease. We use some biomarkers to split subjects into 2 groups: PIP positive imaging or ApoE genes. PIP image measures the accumulation of amyloid and is a clear sign of developing Alzheimer's disease. For ApoE, if one carries such gene, one will have higher chance to develop Alzheimer's disease. To test the group-wise difference, we train 2 DCM models for positive group and negative group, and then compute the distance between the 2 groups. And we shuffle the subjects to form the null distribution of the distance between models, and see if the original distance lie in the extreme end. We do this testing fiber bundles by fiber bundles. We found several fibers which are different between groups, and the results coincided with other research results. The main benefit of the proposed model is that our model is more sensitive to the macrostructure change that can be applied on preclinical Alzheimer's disease. Most other results are based on Alzheimer's disease subject or MCI subjects that have already developed the sign of Alzheimer's disease. We apply our method on both local dataset, ADRC dataset, and another dataset from WashU. Next, I will show Chapter 3, Flow-Based Generative Model for Learning Manifold to Manifold Mappings. Let's recall DTI and ODF. We know that ODF has better angular resolution, but requires much longer scanning time. Can we use deep learning model to generate ODF based on DTI? Well, the first attempt will be using the convolution model, but it turns out to be very blurry here. A better solution is to extend the generative model to manifold space. In order to generate sharp ODF images when given information of DTI, there are several types of generative model such as VAE, GANs, and normalizing flow. Among all these different methods, normalizing flow requires only one neural network. Thus, it is easier to be extended to manifold space. For the normalizing flow model, it uses many invertible blocks of network to map input data into latent Z with known prior distribution. And when generate new data, just sample from latent Z, we can calculate the log likelihood of data X using prior distribution of Z, and the determinant of Jacobian matrix between Z and X are shown here. If the Jacobian is a triangular matrix, the determinant is easy to compute. There are three basic structures for the normalizing flow-based model, called ACNorm, one-by-one convolution, and the affine coupling layers. And we can use similar operation defined before on manifold-valued data to extend the original blocks. This is the modified version on manifold. The major challenge will be defining the projection between tangent space and the manifold efficiently, and also the distribution in the latent space, which is also a manifold, is hard to compute. Go back to our main goal, which is to generate ODF based on DTI. Since directly generating is not good enough, we first invertible map DTI or ODF into the hidden space where the distribution is Gaussian, and then we can define the transformation in the latent space. For the experiment, we apply our model on the HCP dataset, which contains more than 1,000 samples. This is the generated ODF from our method. The fiber bundles are preserved well. Also, to verify if our method can preserve the difference between groups, we apply the permutation testing on each voxels, similar as before. Then we apply the same test on different voxels one by one. As shown here, the ODF performs as the ground truth. The color highlights the group-wise different voxels between gender. Compare with FA and the input DTI, our method can preserve the group-wise difference for the generated ODF. The above two chapters, we work on space of manifold-valued data like DTI and ODF. I will concentrate on the covariance matrices in chapter 4. Let's consider that we want to train a robust neural network. Consider that we have a base classifier f theta. The goal is to certify that for a given x, we cannot find any adversarial point within some L2 ball. If x is far away from the boundary, for the delta perturbation shown here, the perturbed data will also be classified as cat by f theta. However, things will get worse as x is closer to the boundary. Here, we can find a perturbation delta to mistake the classifier. If instead of directly consider the basic base classifier f theta, but we consider the smoothed classifier with averaging some neighborhood, since x plus delta here has more neighbors being cat, the classifier will be smoothed as cat. The boundary of the smoothed classifier g theta will be smoother than the base classifier f theta. Cohen also gave a theoretical guarantee that within some L2 ball, there will be no adversarial samples for the smoothed classifier. What's the problem here? The problem is how to train a robust base classifier f theta so that we can have a more robust smoothed classifier g theta. As the smoothed classifier will need to smooth over some neighborhood, the first attempt will be sample some perturbation samples around the input x to see what the output of the network will be. We first sample an epsilon and add it to the input x, pass it through the network. We can have the output of the network u theta x. Then we sample another epsilon and pass it through the network again to have another u theta of x. And we keep sampling. If we sample enough epsilons, we can have the region of where the output can be perturbed intuitively. If more than half of this region is classified correct, the smoothed network will be robust. This sounds plausible if we can sample enough samples. But by the incentive transformation theory, it would require 2n plus 1 samples for an n-dimension data to make an accurate estimation. For 2D data, it requires 5 samples. For 3D data, it requires 7 samples. But for ImageNet data, the dimension is too high that requires more than 300,000 samples. On the other hand, if we can measure the distribution directly instead of using samples, we can break the dependency of the dimension. Let's first look at 1 pixel of the input. If we track all the perturbation epsilon and visualize it on the axis, since epsilon comes from a normal distribution, we can have a distribution of the perturbed data x shown in red. The mean will be the original value of x, which is 1 here, and the variance will be the variance of epsilon. Let's go back to the network. We can measure all the distribution of the input pixels using the covariance matrix to represent the Gaussian perturbation. If we can track this distribution through the network without sampling, we can have an estimation of the distribution of the output u theta x. So, what's the challenge of tracking the distribution exactly? Well, in the last layer, we want to have the distribution of u theta x, so we will need to compute the sigma I. When expanding this equation in the second last layer, as shown here, it will require 3 covariance matrices, sigma, and 3 cross-correlation terms, E, highlighted in blue and red. When keeping doing this computation in the second last layer, to compute the sigma I minus 1, which is highlighted in orange box here, it will require to compute 3 covariances and 3 cross-correlation terms in the third last layer. But for the cross-correlation term in the second layer, which is highlighted in green box here, it will require 4 covariance matrices and 6 cross-correlation terms in the third last layer. Things will just get worse and worse as the network goes deeper. Actually, it will require k minus 1 times q plus 1 of sigma and much more cross-correlation terms in the q plus 1 last layer. As we can notice that the most difficult part is the cross-correlation term E. We need to find an efficient way to deal with it. Let's look at a 2D example where the sigma of x and y to be 1 and E is minus 0.6. If we can use 2 independent random variables to upper bound the dependent x and y, we can leave the cross-correlation term out. More formally, we can consider 2 Gaussian random variables. Assume that we don't know the cross-correlation E between x and y, but instead, we know that the cross-coefficient is less than some value or max. As shown here, when E varies, the probability ellipse changes. We will need to bound all these ellipses. By choosing the distribution to have covariance B shown here, we can bound all the ellipses using this new red ellipse. Using this method, we can remove all the cross-correlation matrices in the network, as long as we can estimate the Rmax. Then the overall computation cost will be linear in the depth of the network, which will be feasible to deal with. We will need to cooperate with several types of layers in the model to track the covariance matrices. Let's discuss about convolution layer first. In the convolution layer, due to the overlapping, there may be cross-correlation term E. Thus, we will need to apply the upper bound method here to break the cross-correlation term to further simplify the computation cost. And for the linear layer, it might be the simplest one. There's no cross-correlation term since there's no overlapping and everything is linear. The mean term has the same format as the directly passing through, and the covariance term is also easy to compute. For the pooling layer, since max pooling requires max operation on the covariance matrix, which is not well defined, we use average pooling here. Thus, it can be viewed as a special term of convolution layer with the fixed kernel weight 1 over k squared and no bias term. Finally, the most headache layer, the ReLU activation. Since ReLU is an element-wise operation, we can first consider the scalar case. Mathematically, there's a closed form of the mean after ReLU activation. For the variance, we know that after ReLU, it will always smaller than the original data samples. Thus, we use the same variance as the upper bound estimation. This can be extended into vector case. The only difference is that we are using the matrix upper bound. This will be beneficial since if the input covariance matrix is identical, the output will also be identical. For the result, we can see that our tracking can estimate the sample distribution very accurate in different blocks of the pre-act ResNet. And on the large dataset like ImageNet or Places 365, our method shows on average 3.7% larger averaged certified radius. The certified radius means that within such radius, there will not exist any adversarial samples. But here we also want to acknowledge that due to we are tracking the upper bound, if the network is too deep, like ResNet 152, the upper bound can be loose and not very accurate. Empirically, we have tested that the layer of 34 is okay and layer of 50 will be on the boundary. Like we will need to carefully tune the choice of the Rmax estimation. Finally, we will work on the property that consists between manifold-valued data and Euclidean data, the existence of distance, and we will show what we can do with those distances. Consider three models. Often we are concerned with its accuracy profile and evaluate how different models are doing in terms of their performance profile on one or more such criteria, such as sensitivity or AUC. But what if we were not interested in simply stopping at accuracy? What options do we have? Well, one common approach is to perform layer-by-layer comparisons of the features learned by the model. This makes sense. To do so, we can simply look at their difference. Okay, but what if we are comparing two different networks and the layers do not have the same dimensionality? In this case, we are interested in capturing their correlation. Of course, for high dimensions, correlation does not work. But there's a well-known tool called CCA that can indeed be used. In fact, just a few years ago, The idea was used to evaluate representational similarity layer by layer, and it works well. Although given the efficiency issue of running CCA during training, the idea is not widely used. There are stochastic versions of CCA in the shallow setting, but their deep version has only appeared recently. The alternative we describe here resolves many of those problems very easily. The idea is distance correlation. Let's review it briefly. Consider that we are given 3 samples. A simple intuition is that for those 2 samples close to each other in one domain, we want the distance between such samples in another domain to be small. And for those pair of samples that are farther apart, we want the corresponding samples in the second domain to also be far away. So we can measure the similarity between distance pairs instead of samples and see how far we can take this idea. In fact, distance correlation asks us to do exactly this. We need to compute the distance matrices between the given samples, and then compute the correlation between those 2 distance matrices. Theoretically, if 2 random variables x and y are independent, then distance correlation will be 0. And if they are linearly dependent, the distance correlation will be 1. A very interesting property of distance correlation is that it does not rely on the dimension of the variables, in this case, the 2 feature spaces. The dimension of the distance matrices only rely on the number of samples, and the dimension of the variables are allowed to be different. That's great. When the 2 feature spaces are the same, distance correlation is, of course, well defined. Interestingly, when the 2 feature spaces are of different dimensionalities, the distance correlation is also well defined. Also, the calculation of distance correlation is also very easy if you compare it with what may be needed with CCA. Using block stochastic gradient descent during training, we can have a convergent guarantee of distance correlation. Let's move to the actual use cases of distance correlation. In this chapter, I will cover 3 very different applications to show the power of distance correlation. Let's first look at the diverged training setup. If we use distance correlation to impose that 5 networks to be independent, we can have a more diverse distribution of networks. So what's the benefit of this? We know that we can fool one network easily using adversarial attacks. It might also be easy to fool the second network. In other words, we can fool some models all the time, but it's hard to fool all the networks all the time with the same adversarial attack samples. That means by constructing an ensemble of those independent networks, the overall model can be more robust. Let's consider another use case, disentanglement in the latent space. For the encoder-decoder based model, we can encode the input images into the latent space and then recover it back. In the latent space, we can ask that those 2 nodes to be independent to each other. This is called disentanglement. You will see immediately that we can use distance correlation to measure the independency. In other words, if we do so, we can make sure that the latent representations are disentangled. Finally, we can also work on the novel and interesting use case. Condition one network on another network. What does this mean? Well, let's review what this means for linear regression first. What is the role of nuisance variables on the dependent variables? We know that lung cancer has an association with smoking, age, gender, and so on. But what we really care about is the relation between smoking and lung cancer. So the age and gender are nuisance variables. So we need to control for the nuisance variable to figure out the influence of the main variables, the smoking here. But what if the network itself is the nuisance variable? So the question of removing the random variable becomes, what does one network learn that another one does not? This question, to our knowledge, has not been studied in this form before. Let's see how this task is carried out for linear regression. We find that random vectors of two space x and y, and also the ground truth vector. We can project the vector x on y and only use the remaining vector x minus py of x and measure the similarity between the residual and the ground truth vector. But what if x and y are in different dimensions? We know that distance correlation can handle different dimensions easily, so if we can use distance correlations quite directly in this setting, if we can project the distance matrix A onto distance matrix B, and we only use the residual to compute the correlation, we can answer questions of this form quite easily. This is called partial distance correlation. Bringing this discussion back to the vision space, we can ask and answer questions like, what does VIT learns that ResNet doesn't, and so on. Here we'll briefly review some high-level results. For the diverged training, we show that our method can train more independent network. As shown in red, our method yields representations that are more circle-like compared with the baseline. For disentanglement, our method shows the ability to change several attributes of interest like age and gender using semi-supervised labeling. Finally, for network conditioning, we show that by removing ResNet from VIT, it can still learn meaningful results with respect to the heat map using GradCam. For example, for the first column, we can see that initially VIT is looking at the upper right part, while ResNet also look at that domain. But after removing the information of ResNet from VIT, the new VIT model is looking at the lower right part of the image, which is not focused by ResNet. For the future work of this thesis, we will focus on an application project. For the medical domain, we can always use a linear regression model to predict the diagnosis. For linear regression model, we can always remove the nuisance variables like age, gender, and others. But what if we want to control one image out of another image? In this sense, what extra information is in T2 weighted image than diffusion weighted imaging? In the linear regression setup, there's a toolbox named biological parametric mapping. However, recently we are using CNN models to apply on the neuroimaging data. In this case, what one image contains that another image does not requires to condition on one neural network. Thus, BPM will no longer work. But with the help of distance correlation, we can answer such kind of question like, is T2 weighted image always needed even if we have DWI already? What extra information is obtained in one imaging than the given DWI? We will focus on this application of distance correlation into this problem and show the application-wise contribution in my dissertation. Thank you all for your attention. And any questions,